question, how to teach power electronics. Okay. Let me tell you one answer and then we will go through why I am giving you that answer. Let us say I have a box. This box has a efficiency of 1. The box has a output of 20 volt and 5 amps, and the input to the box is 5 volt. This is a 5 volt battery basically. So, can you find out DC? They all are DC. Okay. Can you find out the current if efficiency is equal to 1? It is a box. Okay. So, how did you calculate? You actually calculated the output power, which was 100 watt. The input power is also 100 watt because efficiency is equal to 1, and then you calculated the input current to be 100 divided by 5, which is, that is the answer, correct. So, let us say this is not 5 volt, let us say this is 230 volt AC, 50 hertz. What will be the current? This is the first example. Second example, it is a AC voltage and power factor is 1. I mean, assume power factor to be 1. Power factor 1 means the input voltage and input current are in phase. So, what is output is a DC, input is a AC. No, 230 is AC is RMS, right? Hundred by 230, so whatever that is. So, is that the RMS current or RMS current? Okay. So, have you seen something like this in real life? 230 volt AC is being converted to a 20 volt DC. Where? Laptop. Laptop chargers are generally 19 volt, 19.5 volt DC. But if you hold a laptop charger, is it cold or hot when it is working? Hot. Hot means energy, some loss must be there, right? Some loss must be there. That means that efficiency of 1 that I am saying may not be true, right? So, efficiency is not 1. So, we are saying that efficiency is something else. So, let us say it is 0.9 or 0.95, depends on that. Now, the idea of power electronics is to design this box. Okay. So, I gave you 2 examples. In the first example, there was a 5 volt battery, 20 volt output. In the second example, there is a 230 volt AC supply and 20 volt output. And both these examples actually you have seen in your real life. You have seen in your real life, it is not like from here I am taking these examples. It is something that you have really seen and really believe that that is there, and you have. So, my first question to you was, what is power electronics and how to teach power electronics, right? This is power electronics. Okay. The power electronic is the subject where we deal with converting one type of power into another type of power with a efficiency of nearly equal to 1, that is all. Okay. So, now let us forget this, I will come back to how to teach power electronics. So, did you get anything? Did you understand what is power electronics now, or got a flavor of what is power electronics? Okay. So, I will just go back 5 minutes to my life, into my life, and start all over again. So, when I started telling you what is power electronics, there are certain things I did. The first thing is, I asked you a question, because unless there is a question, there is no answer. In a class, there has to be a question. What are you expecting from me? When you come to 360A, which is power electronics, you want to learn about power electronics. If you want to learn about power electronics, there has to be a question, and that is what I should be answering. So, first thing is there was to be a question. Second thing is, whatever the question is there, has to be related to real life. It cannot be from the air. Okay. So, the reason I felt that there is a connection you can establish. Did you really feel a connection like what Professor Harish was saying, in a class you have to feel a connection to whatever is going on, right? Did you feel with this example, did you feel that there is a connection between what is being taught and what I should learn? Oh no, you did, right? So, that is precisely what he was talking about. There has to be he was talking about an experiment. Okay. This is an experiment. It is an experiment, right? It is a real life experiment, where I know that I have a laptop charger that takes 230 and gives you 19.5 volt. I want to know what is inside it. That is the question I am trying to answer, right. So, when you teach to students, the first thing is that you have to first establish a question, okay. And if the students feel a connection to that question, then they will start listening to you. Okay. Then you do not have to tell them the answer. Okay. So, no one taught me how to run 100 like Usain Bolt. That is why I never run like Usain Bolt, right. But what my parents taught me is how to walk. They told me the fundamental principle of walking when I was a kid, to all of us, right. You do not need to teach students how to run. A person who wants to run will run, do not worry. You have to tell them how to walk. So, when a student come into the class in the introductory level, they want to know what are the principles that are there and what are the principles they can use in their life. Okay. If we start teaching our students how to swim, how kid, I am a newborn, I am 2 years old. The first thing my father will teach me how to walk, not how to swim, because if I know how to walk, later if I want I can know how to swim. Okay. So, what I am trying to say is that a question has to be first asked. The student or the people who are in your class has to establish a relationship to that question, so that they can feel like what he was saying, that oh, you should long for that answer. You know that the answer is somewhere, but where is it? What is that I need to know to get to that answer? Okay. So, in this case it is power electronics, you have to know the answer from. I mean, what is there inside a power electronic converter, what are the principles that are being used in power electronics, all these things you have to kind of learn, right. So, first thing is when you teach a class, the first thing is that there should be a question. The second thing is that your students should establish a connection to that question. The third thing is that you should tell them enough so that they come to an answer. You do not need to come to an answer. It is not your job to come to an answer. You have to tell them the principles that they will use to come to an answer. Okay. So, and always try to tell examples that they can relate to, otherwise they will not be able to do it. So, what I have done is, I have printed out some of my syllabus. Okay. I will talk a little bit about the syllabus, you can just pass it on, and I will tell you why I have printed out this syllabus. No? Just pass it on. Pass it on. Okay. So, when power electronics is taught to us, and that is one of the major reasons why our students do not have interest in the class. Okay. Whenever it is being taught, the professor forgets to establish a connection, okay. And the connection comes from the fact that the student, you have to realize that I can use this somehow in my real life. Okay. Whatever you are teaching, if you cannot use it in your real life to earn money or do business, then it is of no use to us. In other words, I mean, that is the nature of it. I mean, most of us actually want to learn something that we can use in our real life. If you look at my course structure, have any of you taken power electronic course? Okay. What was taught to you? Any device that was taught to you? Thyristors. Everyone was true? Okay, that is the problem. Thyristor is one of those components that is not used anymore. Why are we teaching people thyristor which is rarely used? Okay, it is being used in some HVDC, very high power system, but most of the time the power electronics that I am talking about, which is a laptop charger or some kind of charger, MOSFETs is being used, okay, IGBT is being used. So, that is why when you start with a thyristor and start explaining these complicated circuits, they already lose you. They say, what is that? Where will I use this? Okay, they will remember some equations and then do well in the exam. That's about it. But they cannot feel that connection, right? So, if you look at the second box, fundamental of power devices. Okay. So, here we go through power diode, power MOSFET, IGBT, silicon carbide devices, GaN devices. IGBT is also becoming extinct, by the way. In another 5 years, IGBT will be gone. It will be replaced by silicon carbide MOSFET. Okay. You can now imagine, actually we are teaching thyristor, which is like probably not being used anymore. And then let us say somehow you start using IGBT and start teaching IGBT. In another 5 years it is gone, the student cannot use that device. So, why not teach something that they can appreciate and use, and they can see in their real life. I mean, they are more likely to see something in their real life. I mean, like when I was a kid, I was taught to walk, or my father taught me to walk. The reason is that I will use it in my real life. He never taught me how to swim, because if I want to swim, I will swim, okay, once I grow up. Same is true for a introductory undergraduate student. They are like kid, and you are their parent, and you are trying to teach them something that they can use in their real life. If you start teaching them something that they cannot relate to, why will they do it? I mean, they will not have interest. They will just be showing you interest in the class, and when they go out, they will say, I mean, what is this? Kuch padha diya unhone, right? So, that is why. So, you have to figure out what is to be taught, okay, and then teach them the basics of that. Now, that brings us to a very big question. How do you know what is required to be taught? That is a question, is not it? So, I told you that, okay, you go to the class and teach them what they should know, okay, or what they can use in their real life for their job or for whatever it is, right. So, now the question is, how do you know what is good for them? Any answers? How do you know what is good for power electronics? What should be taught in power electronics? How do you know that? Any ideas?
The principle of switching on.
Principle of switching, okay.
Any device will implement that only. How we can convert AC to DC, AC to AC, about the commuter parts.
Okay. Any other idea? Okay. I will go one step forward. Actually, the way I do it is, I will actually go to the application. Okay. Let us say when I was telling this, first thing I told you is that it is a rectifier, which is used for 230 volt to 19.5 volt to charge my laptop. Okay. From there I will start, then I will start introducing what is inside it. Slowly I will go back, right. So, now how do you know what needs to be taught? That was the question. The way you know is, you kind of look around. Okay. So, there are companies that build this stuff. Okay. So, you go to what are the things that we use in our real life that has power electronics? UPS has power electronics, rectifiers have power electronics, home inverters have power electronics, and battery charger, SMPS, they are power electronics. So, you know all these things. Okay. So, go to the application and then go back from there. What needs to be taught to and once you start exploring what is inside that box, you will see that thyristor is never used. So, if it is never used, why are you teaching that? It is not used. Okay, I understand that they should know the principle of thyristor, but that should not be 75% of the class or 75% of the time of the class. 40 lectures, for 30 lectures we are explaining them how to design rectifiers, 12 pulse rectifiers. These names you have heard? What are we teaching? Why are we doing that? Okay. You want to do that, but do not spend a lot of time. I mean, yeah, introduce them that there is a 12 pulse rectifier. This is how it works. It works when it is 3 phase, and then just tell them whatever the fundamentals are. So, that will only happen when you go from the practical point of view. There is an UPS. What is there inside an UPS? So, what are the things I need to know to teach students what is there inside an UPS? So, if you go through power electronics a little bit more, you will see that power electronic consists of a power stage and a control stage, which is kind of controlling the thing, and the input comes from here. So, our concept of power electronics right now in all the books that we read is they will only talk about the power stage, they will never care about the control stage. In fact, control stage is the one that is really important for us. For a fan, what is important is not whether the fan is running or not, important is whether you can regulate the fan or not. Okay. So, same is true for your laptop charger. So, why does it take only 30 minutes to go from 0 to 80% of power or 90% of power? After that, after 1 year, 1 hour also it will be going to 95%, 96%, slowly it will charge. Why? Why is it doing that? Okay, that means there is a control inside that will initially, when the SOC state of the charge of the battery is low, it will charge using a current source, so that the charging is fast, and then it has to convert to a voltage source. The reason is that when the battery is fully charged, the resistance of the battery is kind of high. If you put a current source, loss will be constant. So, it will heat up. That is why we charge with a voltage source. So, there is a control system inherent in that box that is converting that. Okay. So, what I am trying to establish is that in all power electronic converter, there is a power stage, there is a control stage. Okay. That has to be taught. Okay. What is there in the power stage? MOSFETs are there in the power stage, IGBTs are there in the power stage, silicon carbide MOSFET, GaN MOSFET, they are there in the power stage. So, just MOSFET, can you drive the MOSFET? No, you need a gate driver. Why do I need a gate driver for that? So, then you kind of go one by one. So, if you establish this connection with your students, then they will have interest in what they are learning. If you are just doing that for fun, that is fine. The thyristor will teach and then come back. So, as a principle in IIT Kanpur, I do not know about other institutes, in IIT Kanpur we always do that. We have done away with thyristors, okay. In power electronic courses at least. Me, Partha, Sandeep Anand, we are all part of power electronics faculty group. So, we will not be, we will be introducing you to thyristor, but not more than that. Okay. So, so that you can relate, people can relate to what is going on in real life. Okay. So, what is the summary of this lecture? Summary of the lecture, what did you learn? One.
We need to teach the student.
Please.
We need to teach the student which is really important to them, which is going day by day to life.
Okay. Second.
We need to teach the student the topic which are application based in the real environment.
Do you agree with that?
Yes, sir.
Okay. Third.
That top to bottom, we must first tell them about the real devices that they use in the real world, and then how they are fabricated, and that will arouse the interest. Gradually remove the abstractions from there, and then they will really appreciate or have interest in those subjects.
And start with a question. Okay. So, because there is no question, there is no answer. Okay. Like I was very fascinated by what Professor Harish was saying. I also saw that there were different lights. Me being a professor here for some time, I also did not know why these lights are there and how to remove them. Okay, that is the question, right. And then once you know the question, I will find the answer myself, Okay. I will read things and try to find the answer myself, and if I cannot find the answer and somewhere I will be stuck, that is precisely where Dr. Harris comes into picture. So, I will ask him that particular question, that I am not finding this answer, what do I do? Then he will tell me that you do this. Okay. So, the job of a faculty or you as a faculty is not to show them the way, but tell them that you go on this way, and when they get stuck, the way is like this, right, goes like this and like this. So, in that point you will be there. Right turn maro yahan pe. Okay, so otherwise you will go out. Okay, so that is the job of, you are like a traffic police, right. Any other things you?
Do you also teach the hardware aspect of hardware design?
Yes. So, see, in a course, in our power electronic course, there will be 100 students, okay, in undergraduate level. So, of course, we are not able to cater to the needs of 100 students. We can, but we have just not put that much energy into it. But what I generally do is, I use PSpice, like whatever I have shown is there, that you can actually download a version of PSpice, okay, and we in the class give them examples of designing these converters in PSpice, real life converters, like they will really put a MOSFET there, they will really put a gate driver there and try to simulate how the device will, how the converter will operate. And once they have some form of understanding, towards the end we will have a demo class. I will actually take a same thing that they have designed and show them that, you see, you designed this, now I am putting this, you see the ripple here, what was the ripple you were getting. They will say, oh, from 0 to 5 amps it was triangular, then I will on the scope I will show them that this is triangular, you can see the values. Okay. Yeah, I understand that everyone should do this and learn by themselves, but being a 100 student class, it is very hard to, unless you are I mean you are more methodical, it is very hard to perform experiment for 100 students, that is to this kind of experiments, where you have to design converters and stuff like that. But yeah, so we solve this problem this way, they do a PSpice simulation, then we in the end, when they have an understanding, we show them how the actual behavior is. Any other thing?
Generally, students get mess up with the phasor diagram. What are the best way to teach them that they can confuse?
You ask them to design the do the phasor diagram themselves. See, when I teach, or when we teach, phasor diagram is a basic electrical engineering thing, right? Basic electrical thing. So first question I will ask to you is 230 volt 50 hertz. Can you draw this waveform in time domain? That is the first question. Can you draw this in time domain? Draw it in time domain with t as in the x axis. Draw this waveform 230 volt 50, that comes from our input. So, can you draw that? How draw? तो पीक कितना होगा इसका? That is where you are wrong. 230 root 2. So, that is the first thing you have to know. Okay. So, 315 or something like that. So, now the question is, if I draw this as a phasor, how do I draw it? I do not have a t equal to 0 t, nothing is there. So, how do I draw it? Phase reference. Let us say this is my reference, okay, and this is where I have to draw this waveform. How do I draw it? Zero is anywhere, right? You just take whatever is 0, right? Horizontal is 0 generally. Okay, so you can say that this is my 0. So, this will be my phasor. The question is, what will be the magnitude of this? So, this is where, like if I say it is 230, if Professor Harris is talking about, it will be 350. So, there is a confusion there. So, in power engineering we generally use the RMS, in electronics we will generally use the peak. Okay. So, that is something that you have to understand, that who is your audience you are talking to. But If you know both the things, then you are fine, right? Right, like Tendulkar, like he knows all the shots, whatever you want. So, now the second question: if my phasor is not 0, it is 30 degree, how do I draw it? I will say that this will also serve as the 30 degree phasor, but it depends on where you take your reference, right. So, if I say that this is my reference, this is my 30 degree, okay, that's fine. Now, we say that okay, this is 0, my current is 5 angle 30 degree. How do I draw the phasor? So, from here, so it's rotating in the other way. Okay. Now, I say that it is 530 degree, but phase this frequency is 60 hertz. So, if someone asks you to draw this as a phasor diagram, what do you do? How do you draw? What do you mean you cannot draw? See, do not say that you cannot. You can draw, but you cannot draw on the same phasor. Yes, then you draw two different phasors. You draw the phasor diagram of this. So, what do? You take this and they say that this is my voltage and this will be my current. Okay. It does not matter, this is just taken as 0 degree. Okay. Now, you just teach students this much, you are done. Then you ask some power electronic question and say that you draw. Okay. It will take you 5 more minutes, for because they will be fumbling, they will be doing different things. But when they come up with something, when they are thinking about it and drawing something, and then when you tell them that answer, they will appreciate it more. If you just draw it like that, if I would have said that okay, angle do hota hai, you will not understand. It has to be, everything has to be a question, then only there has to be an answer, right. So, that will be my way of doing it. So, there are many other ways, but yeah, this is my way of doing it. It's okay.
But we cannot define phase difference if the frequency is different.
Yeah. So, that is why there are two different.
30 degrees with respect to voltage.
No, I have said that 0 0 written there. Okay. So, what you are saying is this. Okay, if someone, if student A draws this, student B draws this, will you give a mark? He has to say yes, because it was not your question, it was his question. Will you give mark? If this one student has drawn like that, another who had drawn like that.
The voltage and the current are for the same element.
No, it does not matter, it may be for the same element. We have two phasors, we are trying to draw the phasor diagram. So, someone A student has drawn like it is in the left side, Y student has drawn like it is in the right side. Which will you give mark? Full mark to the student? Yes, you will give. How about you? Confirm? Okay. So, it depends, right. So, what it means is that for that same phasor, what is the 0 you have defined, because they are of different frequency, they cannot be on the same. That does not matter, right. I mean, okay. So, similarly we say that let us say I have a 230 volt thing, right. I take a DC current, 5 amp DC current. That means, I will put a, this is my home power supply. What I have done is that I have put a plug here, okay, that takes a 5 amp DC current. So, what is the power supplied to my equipment? I have some equipment that takes a 5 amp DC current when I plug in 230 volt. 230 volt. 230 volt is this 230 volt that we have. So, what will be the power taken by that? No, power P. Voltage current is given to you. What do you mean resistance? One is 230 volt, it is taking 5 amp DC current. What is the power input? Does the question make sense? Okay. There is a box, 230 volt plug is there, I put that, and when I measure the current, I measure 5 amp DC current. What is the power taken by that box?
230 to 5.
Root 2 into 230 by pi.
Root 2 into root 30 by pi. Any other questions? Let me write down all the answers, so that root 2 into
Root 2 into 230 by pi into 5.
230 into pi
No sir, into 5 by pi.
into 5 by pi. Correct. Okay. Any other answer? A. Answer A. Answer B. 230 into 5. 0. Any other? Any other? Okay. This much. Yeah. So now question is, what is power? Power is voltage. Whatever voltage you have, whatever current you have, you multiply that. Multiply it. You have 230 volt, means you have a 315 volt sine wave, peak sine wave, draw that and multiply 5 to it. So, what you will get is the peak of the waveform will be 315 times 5. Equipment is a some fridge I got, refrigerator. Yes. Some.
It's not a measurable device.
No. It's a refrigerator. Okay, you multiply that. No, you will tell the answer. Don't ask me. Take a 230 volt, multiply 5 and draw the time domain waveform. You understand the question and what to do? We have 230 volt, 5 amp. You multiply that and draw it in time domain.
The time domain of current or power? Current power.
What is current power?
Current is actually DC current.
DC current,
But the voltage we are given is in
AC voltage, and we are trying to find out the power. You have 3 answers written there. Is there any other answer I can write down there?
How it could be possible DC current?
That is what now, it is not possible. That is what I am. You draw the time domain waveform. That is why I said you draw the time domain waveform. Let us go from the fundamental. Okay. See, you have higher learning level, so you said it is not possible. But let us go from fundamental and reach to that conclusion. So, if what is power? Power is actually voltage into current, then average it. So, just multiply voltage and current. You got some sine wave. What is the average of that sine wave? Average of the sine. What is the average of this signal? The voltage that is coming into our average of this, have what? Half cycle, the full cycle? 0. Answer is 0. Why? Answer is 0 because if you have a 230 volt, if you have a 50 hertz, unless you have another 50 hertz component in it, the power will be 0. It is called orthogonality. Okay. That is something that we see in power electronics all the time. That is why we have a different definition of power factor. Normal definition of power factor does not work. Why? Because my 230 volt voltage should have a some 50 hertz component in it, otherwise the average, like I am telling you, what is the fundamental definition of power? Power is voltage times current, you average it out, right. So, I have multiplied voltage and current and averaged out, it is not, so you multiply let us say 5 amp 50 hertz current. So, what will you have is a 5 amp current here. You multiply that, you will see that product will not be 0, because even these both are negative at the same time. So, it will be a positive. So, you will see that this kind of a waveform will get 100 hertz, that will have a certain average. Okay. So, that is the power that you will see. So, that is another learning of power electronics, that a voltage should have the same frequency component in order to have power, otherwise you will not have power, right. Another question, we get 230 volt, we said that the average is 0. Is the average 0? Who makes sure that the average is 0? There is no police, but we always measure that the average is 0. Someone is generating in the like power station, 230 volt is being, or whatever voltage is being generated, it has supplied to me as 230 volt, and whenever I measure, I always see that the average is 0. My question to you is that who is making sure that the average is 0?
Transformer.
Why transformer?
So it eliminates DC to be coupled.
Yeah. So, it comes through a transformer, right. So, transformer will take away that DC. So, that is why every time I measure that, even though no one is there around to see, because it comes through a transformer, my DC has been taken out. I will only see a AC. And remember that if you have a little bit of DC in your inverted wave, it will cause huge amount of problem for you. That is why designing inverters is so difficult, home inverters. When we design home inverters, we have a 12 volt battery, we are trying to make a 230 volt. You have to make sure that it will be 0. So, that is why normally it is put through a transformer. So, that you kind of eliminate that DC, because you are now recreating a waveform, right. What you have done is that you said that okay, part of the time my output will be plus 12 and part of the time my output will be minus 12. You have a 12 volt battery. Now, who makes sure that these two areas are same? Because unless these two areas are same, the average will never be 0, right. So, who makes sure of that? So, no one makes sure, that is why you have to put a transformer there. So, if you open up your inverter, home inverter will always see a transformer inside, and that makes sure that you do not have a DC component in that 230 volt thing.
A question completely out of this. Actually, binary inverters, there will be two types of inverters, square wave inverter and sine wave inverter. Which of them is the better?
Okay. The answer is very simple. When your inverter turns on, do you hear a noise in your fan?
Yes.
That means you have a square wave inverter, you have harmonics. But this is designed to work at 230 volt, you are putting 150 50 hertz.
Higher frequency compared to
So, sine wave inverter you will not see that, hear that noise, but that frequency what is the frequency I can hear? From 0 up to what frequency I can hear? What is audio? 40 kilohertz, 20. Okay, I have tested myself, I cannot hear more than 5K, me. Okay, dogs can hear 10K or 20K or 15K, but I do not know about you, but my ear I cannot hear more than 5. Okay. So, if I put the harmonics in 100 kilohertz range, then I cannot hear, my fan will not make any sound. That is precisely what is done. In sine wave inverter, the harmonics is put at the highest frequency, but in square wave inverter, by nature you can see that if you have a square wave 50 hertz, if you look at the Fourier of that, you will see that there is a 50 hertz, there is a 150 hertz, 250 hertz, all these things. So, that is why they will make sound. Okay, which one is better? That is your answer. There has to be a question, then only there will be an answer, and the answer should come from you, it should not come from me. I should only guide you to the answer. Okay. Anyway, so that is how it is done, or that is one of the ways it is done. Okay. Any other questions, or we can just take?
Sir, actually, we see people do not study that power electronics, but the name is power electronics. Can it be power electrical? Why the name?
Oh, because see, if you look at that is precisely why I drew those two things. So, you will see that in power stage there will be MOSFETs, IGBTs, these are all semiconductor devices, which is electronics.
But we people do not study that.
Then there is a control stage. In control stage, what is there? If you look at my syllabus that I have given you, I will talk about things that we teach here are gate drivers, control ICs. Okay, these are all required. We do design a power electronic. How do you otherwise make sure that regulation happens? Regulation means control happens. I need something, I get something. That control, how does that? So, that requires electronics. So, power electronics means it is at high power and it uses all kinds of electronic component and equipment to process the power. That is why it is power electronics. It has to be, it cannot be electrical. So, fundamentally by nature
Cannot be power electrical.
cannot be, right, because it requires electronics to operate. You open your inverter, home inverter today, you see the motherboard, you will see 10 ICs there. They are required for the thing to operate. Okay. So, the way it was being taught to you is they only teach about power stage, thyristor, power stage, commutation, all those things they cover a lot, but actually that is not important anymore, because we do not use thyristor anymore, we use IGBTs. IGBTs can be turned on by a gate, turned off by a gate. We are not dealing with line commutation. Line commutation means turn on is our control, turn off is God's control. No, it is not like that. The modern devices are turned on and off by us. Okay. So, it has to be electronics. Okay. Sure.